Welcome, Calculus 2 students. We're looking at direction fields and Euler's method today. So let's look at this family of solutions that we have here. In this family of solutions, I see that the equilibrium equation happens to be y equal 2. So I can write this as y of t equal 2 is an equilibrium solution because I see that I have a horizontal line here. These values along the side are my initial conditions, and I can follow a solution from this family. So let's look at an initial condition, say y of 0 equals 3. If I were to follow this path, this solution would look like such, and since this is going to go up there, then I can note that it will continue on up towards infinity. So let's look at this next one. I have as an equilibrium solution y equal 2, so y of t is my equilibrium solution, and they want to know for what initial conditions are t equals 0 the solution's a constant, increasing and decreasing. So of course y of t equal 2 would be my constant solution there for an initial condition of, let's say, y of 0 equal 2.5. This would look like that. For an initial condition of, let's just say, whoops, where did my mouse go? Okay, let's say for an initial condition of y 0 equals, let's just say 1, that would look like this and continue on down. Alright, let's go to our next slide, which tells us how to draw our own family of solutions. So first off, what I need to do is figure out where I have my equilibrium solutions, and that is where my differential equation is 0. So that would be at both 0 and 2. So I'm going to draw that constant. Alright, so I have this drawn for you where this at y equals 0 and 2, I have my constant or my equilibrium solutions, so I have my constants there. Number 2, I'm going to find where my differential equation is greater than 0, and let's just say if my differential equation were greater than 0 in this realm, I would draw those slope curves so that they moved towards these constants, and they would look kind of in an S shape going this way. If, however, I found in this region it was negative, I would make my S kind of in this backwards fashion and go that way. And if this was decreasing, then it would look like this. If it was increasing, then I would draw them as such. So let's go ahead and get that done. Let's figure out where I have my increasing sections first. Okay, so if y is greater than 2, this thing is going to be increasing. So let's draw these. That means it's going to start here and go in that fashion. Get those done. And less than 0, they also need to be increasing, so they're going to look like this. Alright, I know it looks lovely. Notice how these are all increasing slopes here. and these guys are all increasing slopes, and that must mean in the middle here it's going to be decreasing slopes. So these guys are going to do something that kind of looks like this, and I'll get my little family drawn here. Okay, I know that's stunning, and so the 3 was to see where my differential equation, where those slopes were less than 0, that meant they were decreasing. And if I were to just look at, let's say, an initial condition, let's just look at a couple of them. Alright, I'm going to look at initial condition 2.5, and that would follow this, and somewhere in this neighborhood here. That would be that solution for that initial condition. Let's look at one where my initial condition was somewhere between 0 and 2. Alright, let's look at 1.75. So there's 1.75. Let's just choose this one, and we would say that that would look something like that. Stunning. Step number 1 was to find the equilibrium solutions. So I found that if P was 0 or P was 300, I would have my constant, and this will be my T. Next, I'm going to find out where it's increasing and decreasing. I can see that for anything over 300, this number is going to be greater than 1. That means this is going to be decreasing. This section here between 0 and 300 will be increasing because I'll have positive values. And so and anything below that doesn't make any sense, so I won't draw anything down in the negative values of P, because populations that are negative don't make any sense. Alright, I have this thing drawn. Now looking at my initial condition where the population starts out at 50, it would look something like this. Let's look at, get a new color. Population 150, there's 150. So it would kind of look like this. Continue on. And next one. Okay, for 350, it's going to be a little more like this, and continue on. The last question asks us to interpret as t goes to infinity, what's the limit? And I can see that the limit of this is 300 because this population is a stable population with a carrying capacity of 300. Alright, now we're on to Euler's method. Using these slope fields is similar to how a computer calculates a solution to a differential equation, and it is by Euler's method that this is accomplished. So we are going to simulate a computer here, and we are going to use Euler's method to get a solution to a differential equation with an initial value. First up, they want me to break it up into, they want me to do this 2 separate problems. I'm going to do a delta t broken up into steps of 0.2, and I've got to go from 0 to 2, so they're going ahead and letting me know that this will be 10 total approximations, and then I'll plot those points. That's what I'm going to get here. Alright, there is my first approximation. It's given with the initial condition right there. For my next approximation, I'm going to follow this formula here, and for this one my k is 0, so it's going to be my previous answer, plus I'm going to plug into my function my t sub k, so in this case I might just go ahead and say for this one k equals 0. And so this is my u sub 0 plus 1, or my u1 solution. And so I'm going to plug in a 0 for t, and I'm going to plug in a 1 for y. So this would be minus 1/2, and I'm going to get for u sub 1, that's going to be, so I forgot to put in my times delta t there, and then this is going to end up being 0.9. And then I'll go to the next one. K is 1, so I'm going to do U2, and this one will be 0.9 plus, and then I'll plug in my function. My t in this case is 0.4. No, actually this one is supposed to be t sub k, so it's actually the 0.2, sorry. So it's the 0.2 minus, and then I'm going to plug in the u from the previous one, which is 0.9 over 2 times that delta t, and that delta t was 0.2, and for this answer, I'm going to do this for all the rest of them. And yes, this can be tedious, so I went and grabbed the table. You could plug this into Excel or something and it would be a lot quicker. And there's the table for each of these calculations. You can also see that here is the red line is what I plotted, the blue line is the actual solution for the differential equation, and that would be this y of t. They want to know which one is a better approximation if delta t is 0.1, so let's get that one up as well. Alright, so this is the solution if you let your delta t be 0.1 and you have 20 points that you're going to plot here, which would also, I would just want to do this on Excel, and I can see that visually the one where I had the smaller time segments is going to be closer. You could actually compute each of these points and then get the error for each of these points comparing to what the actual solution is. They didn't ask for that. They actually did it in the text if you want to look at that, but it's not necessary, just subtracting to get that error. I'll give you the table. So here we have the errors where they did that subtraction for us. This was the error with the delta t at 0.2, and this is the error with the delta t at 0.1, and you can see that the error was consistently better with those smaller time steps. Alright, and that does it for section 8.2. If you have any questions, see me at the Collaborate.